Okay, so it is my great pleasure to introduce the all-time classic, Karol Węgrzycki, talking about all-time classic results, for rather new results, but for all-time classic problems, Euclidean TSP. Please.
Yes, hi. So this is a joint work with Sándor Debug and Jesper Nederlof. And I will be talking about Euclidean TSP. So what is an Euclidean TSP problem? So in this problem, you are given n points on some d-dimensional space, and the task is to find the shortest round-trip tour that visits all the points. So in this example, we are given this set of points, and the optimum solution to this instance may look like this. So this blue tour goes through all the points and finally closes at the start point. And it's, you can believe me that this is a shortest tour. We can generalize this to d dimensions, but for this talk we will talk mainly about 2 dimensions because it's the easiest to write the pictures on the plane. Right, so what do we know about the Euclidean TSP problem? Unfortunately, it's NP hard, as shown by Papadimitriou, and the best algorithm that currently are working in sub-exponential time to the square root of n in 2 dimensions and sub-exponential for constant dimension by the Berg et al. And unfortunately, you cannot really improve it asymptotically. So these results are asymptotically optimal. So it seems like this Euclidean TSP problem is closed. Therefore, we need to settle for approximation. Right. So let's check what happens in approximation regime. And I will be talking about an approximation algorithm. So polynomial time approximation scheme is an algorithm that for any fixed constant epsilon finds a tour that is only 1 plus epsilon times worse than the optimum solution, and it works in polynomial time. So at the time, it was a very big open problem whether such an approximation scheme exists, even for the plane. And it was resolved by Aurora and Mitchell in late 90s. So Aurora gave a p-task that works in n to the log n over epsilon to the power 1 over epsilon, and Mitchell gave n over 1 over epsilon time algorithm for the plane. At the time, it was such a big result that 10 years later that they received a Google Prize for their accomplishment. And at the time, it was very surprising. Then it was improved. Right, the dependence on n and epsilon can be improved, and currently fastest algorithm is by Rao and Smith. And that works in 1 over epsilon to the power 1 over epsilon times n log n time. And it is, I fixed the dimension d to be n here. So the running time in terms of n is near linear, it's n log n. But the dependence on epsilon is super exponential, is 1 to the 1 over epsilon times log 1 over epsilon. And if we are having actually two different regimes for this problem. So if you don't really care about what is the dependence on 1 over epsilon, then you can even get a truly linear running time by the result of Bartel and Gottlieb from 2013. And both of these results are unfortunately quite complicated and hard to implement. What we have is very simple algorithm that runs in 2 to the 1 over epsilon times n log n, and we also prove that it is optimal. So you cannot really improve the dependence on epsilon in our algorithm. I want to say that the algorithm is very simple. It's only slightly more involved than the original Aurora algorithm, but the analysis is more involved. And we also have a couple of results for Steiner tree. So in the Steiner tree problem, you are given a set of points, and the task is to connect them using Steiner points. So the optimum solution to the Steiner problem for this instance may look, for example, like this. And we also are interested in the rectilinear Steiner tree problem. So in the rectilinear Steiner tree problem, you are only allowed to use axis parallel lines. So the optimal result, optimal rectilinear Steiner tree may look like this. And for that, we claim that actually pretty much the same running time as for the Euclidean TSP. So we show that this Steiner tree problem can be solved in 2 to the 1 over epsilon times n log n time. The same holds for rectilinear Steiner tree. And for rectilinear Steiner tree, we also prove the matching Flower bounds. So for rectilinear Steiner tree problem, you cannot improve the dependence on epsilon by little o. So to summarize our results, we give a very nice new technique that we call sparsity sensitive patching. I will explain later what it is. And for Euclidean TSP, we give a randomized 2 to the 1 over epsilon to the d minus 1 n log n time algorithm in d dimension. And we also prove that it's optimal, assuming something that is called gap exponential time hypothesis, even if you are interested in higher exponents in the n dependence, you cannot get below this 2 to the 1 over epsilon to the d minus 1. And the previous best algorithm was by Rao and Smith from late 90s. So we basically replace this 1 over epsilon with 2 here. For rectilinear Steiner tree, we also prove very similar results. So we give a randomized 2 to the 1 over epsilon to the d minus 1 times n log n time algorithm. And previous algorithm that was claimed is also by Rao Smith. Unfortunately, we were not able to verify that it's correct. And for rectilinear Steiner tree, we also give this 2 to the 1 over epsilon to the d minus 1. Actually, for the normal Steiner tree, we give 2 to the 1 over epsilon to the d minus 1 n log n time algorithm. And the previous algorithm that was claimed was by Rao and Smith. And they also claimed that the results worked for rectilinear Steiner tree and for Steiner tree. But very recently on Stock, there was a paper accepted by Bartal and Gottlieb that claims slightly worse running time. So the situation is rather complicated. But fortunately, our algorithm works faster than both of these results. So we somehow clarify what was going on here. There is no unclaimed results now. Yeah, we closed we basically close what is known for TSP and Steiner tree and rectilinear Steiner tree in most of the regions. Right. Any questions so far? Oh, okay. So before I begin, I will tell you why it's actually important that we are working on this. Why do we improve the dependence on epsilon? The epsilon should be a constant, right? Right. But I want to say that this is actually a very classical result and a very fundamental problem. At the time when Aurora showed this result, it received a Doodle Prize. And also this Aurora and Mitchell algorithm are the basis of several undergrad courses. I believe that everyone here saw what is how the Aurora algorithm looks like in this crowd. So it's a very natural question whether we can actually get something better out of this well-known algorithm. And also it has plenty of applications in manufacturing and logistics. You can check that on Wikipedia. So it's natural to think, well, what's the best algorithm that I can get, even if I want to have non-constant epsilon. Right. The second argument is that it's optimal. So there will be no incremental improvements over what we have done. Right. We complement our result with a conditional lower bound and show the tightness in almost all regimes. And I want to point out that this f of 1 over epsilon dependence and whether you can get an optimal results is actively researched for other problems, like, for example, TSP in planar graphs or independent set in planar graphs. We all have the fastest possible epitasis in their regimes. But for example, by Marx from 2007, and basically what we are doing in this paper is to complement, is to move this line of work to the other classical problems. The next thing is that actually our algorithm is super simple. I believe that our algorithm was implemented several times. So to apply our algorithm is to just one small modification to the original Aurora algorithm, and you will get a fast solver for Euclidean TSP in practice. Unfortunately, Aurora algorithm is not really implemented, so I suspect that heuristics that don't guarantee you any solution still may be faster. Other reason is that previous epitasis were complicated and several details were missing, and not all of them were published in the full versions. And, I don't know anyone who understands how all of them work. So now you don't have to. There's this nice simple new argument that enables you to resolve all the problems. And actually, I want to claim that this new technique that we are introducing is transferring to all these new other problems. We don't need anything that is called spanner to get epitas. So this allows us to work for Steiner trees, and hopefully it will generalize to other problems in the plane. Right. So that's why I think it's really cool. Now let me present to you the roadmap of what I want to plan and what I want to plan to talk about. So first I will talk about this original Aurora's algorithm, and we will recall what is basically going on there. And then I want to tell you about this Rao-Smith algorithm and why, what new ideas they had, and what actually prevented us for 2 years to improve upon them. Like, we really tried to look underneath this Rao and Smith algorithm and try to slightly get rid of the slot 1 over epsilon time algorithm, but why it's really hard to get below this running time by using their techniques. So at the end, what we have done is basically go around it and go back to the original Aurora's algorithm and use this, and we introduce this new sparsity sensitive patching technique, which basically has nothing to do with Rao and Smith algorithm. And after that, I will present to you this how easily you can use this technique and get some new algorithm. And then actually what is really nice is that I will prove to you that this works. The proof is slightly more involved, but I will try to not wave my hands. I will present to you the proof in 2 dimensions. It's really nice. It was originally 10 pages, but we brought it down to 2 slides after 3 months. And then I will present to you the lower bounds, the Gap-ETH lower bounds that show that these algorithms are optimal. Okay, so we are starting right now. So buckle up and let's go for this ride through the TSP regime. Right. So now I will present to you this Aurora's algorithm. So we have two assumptions that are very easily to enforce. So first assumption is to assume that points are inside L by L box and all the coordinates of the points are integers. So to assume this first assumption, we basically, to second assumption, we basically move this point slightly with something that is called snapping to the grid, and assume that these coordinates are integers, and then we can assume that they are inside this L by L box such that this is N by epsilon grid, basically. So these are the two assumptions that we are having right now. Okay, and the Aurora had very natural now, but ingenious idea at the time. He introduced something that is called quad tree. What is a quad tree? And he introduces a randomly shifted quad tree. So first of all, he guessed this middle point. He randomly selected this middle point, and he dissected the space into four squares. Right, like on this picture. And quad tree is basically this dissection of the space such that inside of one cell of a quad tree, there is at most one point. So for example, when we are here, we are basically done. We don't dissect the space anymore, but when we are here, we are having also one point, so we are also done. But here and here, we are not done. So we continue to dissect this space. So now we are at the level 0, and we continue to dissect to get a level 1 cells. And these are the level 1 cells in which we are basically done. But here we have 2 points in this cell, or 3 points in this cell. So we need to dissect the space further, and we end up with the second level of a quad tree, and we are now done. There's no point to no space to dissect more. So quad tree is basically this dissection of the space, so that in one quad tree cell, which is this cell, for example, we only have 1 point. Okay, and a question to get the idea what a quad tree is. Okay, and then comes the ingenious part of Aurora, which is to introduce something that is called portals. So for on each cell border, he puts log n over epsilon portals. So here he will put log n over epsilon portals, the granularity that I call G. Here it will be G portals for each level of a quad tree. So in here it will be log n portals, and in here there will be log n portals. Okay, so if you go down at the quad tree, the number of the portals that you are seeing is actually always the same, but the precision is increasing. So this here you will have super low precision, but if you go down, these portals will be super close to each other. Okay, so this is a portal, just a point on an edge. And now let's define what is a portal respecting segment. So segment is just an edge, or segment is just a line that connects 2 points, and this line is not portal respecting. So because it is crossing a quad tree cell, not in the portal. So we can make this line portal respecting by bending it. So this line now is portal respecting because it crosses a quad tree exactly through the portal. Okay, and now comes this ingenious structure theorem of Aurora. Structure theorem says the following: if I have the optimum solution to TSP, let it be pi. This blue thing is the optimum solution to the TSP problem. Then there exists a portally respecting solution. Let's call it green. Let's call it. This is this green solution, and it's portal respective because it crosses this quad-3 cells only on the portals. Then this difference between this blue and green part, an expectation is taken over the shifts of the quad-3. Recall that we have randomly shifted the quad-3 at the very beginning of the algorithm. Then you basically don't lose too much, right? In this portal, you can restrict yourself to find only a portal respecting solution, and you will get a nice 1 plus epsilon approximation. This is a structure theorem of Aurora. Okay, so now we know that we can look only for the portal respecting tour. So what happens now is basically we need to find this minimum length portal respecting tour by involving this DP. Okay, and let's now bound the time to compute this portal respecting tour. So we will start from bottom and we will go top with the DP. So what is actually the solution that we need to define this dynamic programming? It's basically this shortest path cover. So if you look at this quad-3 cell, maybe this example is wrong, but it could be like this solution is going somehow divided into this for this cell into a path cover. For example, here in this big cell we have 2 paths. So for a given matching and for a given we need to find the shortest path cover that is portal respecting. So here is a cell of a quad-3. What we need to do is we need to guess through which portals this path cover will go through. Let's say these are these black portals, and we need to select them out of log n over epsilon portals. That's the number of equispace portals that we have selected. And also what we need to guess is matching on these portals. So crossing matching. We only are interested in non-crossing matching because we are solving the TSP. Okay. So the number of states in this dynamic programming is number of cells, which is n log n. This is the number of cells in this quad-3. As number of guesses of this matchings is n log n over epsilon 2 to the g actually, and number of possible non-crossing matchings is also 2 to the g. So at the end, what we are ending up with is n log n to the 2 to the g, which is n to the 1 over epsilon time. Okay, this is a classical Aurora's algorithm. So now let me prove to you this structure theorem and see how he proves this, just for the sake of completeness. And any questions about the Aurora's algorithm? Okay. So now let me prove to you this structure theorem. Actually, I will prove something more. I will prove something more. So now we start with a nice definition. Definition is the tour is light. And what is a light tour? Tour is light if basically it crosses this quad-3 at most r times. So this tour is not r light because it crosses this quad-3 edge 4 times. Right, but if it crosses every edge of the dissection at most r times, then it's too light, r light. And for example, this tour is too light because every edge of the dissection is crossed only twice at most, right? For example, this edge is crossed only once. This edge is crossed only twice. So yeah, this, and you can check that for every edge of this quad tree, this tool is just only twice. Yeah. So this is what I mean by lightness. It's basically how many times this tool is crossing this cell. And the structure theorem is that if I put these portals to be log n over epsilon, then with sufficiently high probability, I will have a portal respecting tool that is only 1 over epsilon light. And the cost of this tool is not large comparing to the optimum. Okay, so if I had this tool, I will now have this tool, for example. And the proof consists of 2 steps. So first step is to apply this patching procedure to this optimum solution to make this crazy tool light. And we can guarantee it, for example, like this. So you have this tool, it crosses this edge of a quad tree less than 1 over epsilon times. Then what we basically do is we move these crossings slightly infinitesimally close to this edge to the portal, right? And now, because the tool originally crossed this edge only 1 over epsilon times, then this modified tool will also cross it 1 over epsilon times. So if the tool is crossing it less than 1 over epsilon times, we can also make it light. And the cost is basically the length of this board divided by g. So basically the distance between portals times the number of crossings. Because for each crossing, we move it to the closest portal. Okay, but it can happen that tool is crossing this edge more than 1 over epsilon times. So then comes this something that is called patching lemma of Aurora that we expand on. So if the tool is crossing this edge more than 1 over epsilon times, then Aurora does modify this tool like this with something that is called patching lemma to make it cross only constant number of times. And the cost that he has because of this patching lemma of his is only 2 times this border length. Right? He instead of going many times through this through this edge, he connects the subsequent crossing points to each other, and the same on the bottom, and then connects it up to the right. And this way, he modifies this tool to only cross it only once.
Do I get corrected? The order of the visits of the terminals is changed using this in this patching? Okay, yeah, fine.
Yes.
Just wanted to make it clear.
Yes, but it's still a solution to TSP. Okay. So we have now modified this tool to be 1 over epsilon light, but we didn't have any guarantees on this new cost, right? In this situation, the cost was 2 times the length of this border. So what Aurora shows is basically that if you only look on expectation on this one crossing, on a single crossing, that the cost that he incurs is less than epsilon. And then if you look at all the crossings on the whole dissection, you will increase this length of this tool by only epsilon times the length of this tool. I will not show you this, because we will see a really more involved argument in our proof. But his idea is to look at this expected cost of single crossing. And that's really important idea for us. Okay, and so now let's look at the number of the running time of this dynamic programming. So he has n log n cells, and the number of states is now number of portals to the power of 1 over epsilon, because from these G portals we are selecting 1 over epsilon portals. And that's this way Aurora achieves n log n divided by epsilon to the power 1 over epsilon n time. Because what I have showed you here is better structure theorem than on the previous slide. That's why the running time is better. Okay, cool. We have seen the Aurora's algorithm here, and now we are heading to the previously best Rao and Smith algorithm. Okay, Rao and Smith had very nice idea. They used something that is called spanner. Geometric spanner is basically a graph on the plane, such that if you look at any 2 points, U and V, for example, then the distance in this spanner is a good approximation of the real distance between these points, of the distance on the plane. So that you can look only at the edge distance in this graph G of this spanner to have a good approximation of the real distance. And what's important is that this is a subgraph of G. So there are no new Steiner points in this spanner. It's just the spanner that uses as a vertices the original vertices of your instance. And this is what is known as 1 plus epsilon spanner. It's a geometric graph. So to get an approximation in this graph, you would got that the shortest path in this graph is this, and it would be 1 plus epsilon approximation of this distance. Okay, now the nice claim about the spanner. So to solve the TSP, you basically need to look at the spanner, and you will get a nice 1 plus epsilon approximation. So if you you can to solve TSP, you can just look at the graph now and get rid of this plane and try to solve this TSP approximately in the spanner, and you will also get this nice algorithm, but you would lose some polynomial factors, and that's where the next idea comes. So the second idea of Rao and Smith actually claim is that you can create something that is called light spanner. What is a light spanner? Light spanner is the spanner such that the total weight of all these edges, if you sum it up, you will get something that is some function of epsilon, so some polynomial 1 over epsilon, longer than what you would do if you would compute minimum spanning tree. Okay, that's useful because minimum spanning tree is a constant approximation of TSP. Okay, so the main insight of Rao and Smith now is that if you have the spanner, you can patch it in the similar way to Aurora, and guarantee that if you have a randomly chosen quad tree and you have completed this light spanner, then you can patch it like on this figure and get that it will be crossing every edge of a quad tree at most polynomial in 1 over epsilon time. So the idea behind this patching procedure is basically if the spanner is crossing the quad tree edge less than 1 over epsilon to the 4 times, you don't have to do anything. And if it crosses more than 1 over epsilon to the 4 times, you can basically do this patching lemma of Aurora on the spanner and make it cross only once. Okay, this doesn't seem useful, but what they prove is that if you do this patching procedure, this green, then this total length of this green edges is at most epsilon times opt. That's the cool thing about this spanner and this patching procedure. So now comes the super nice idea of Rao and Smith, and it's basically to say that if you combine this plane 1 and this new insight, then you can basically direct where the portals are. And if you put these portals at the crossings of spanners and quad 3 edges, you will have only 1/epsilon to the four portals. Yes, because we now know that there exists a 1+epsilon approximation that uses only these portals of Aaron-Smith. And now note that this is a super dramatic improvement of what Aurora had, right? It is a constant where this Aurora argument had log n and many portals always. So just to recall, this theorem of Aaron-Smith is that you can get this patched spanner. This spanner contains 1+epsilon approximate TSP. And it intersects every cell at most 1/epsilon 4 times, and so there exists, and I didn't mention this to you, but there exists an approximate solution that will intersect every quad 3 edge 1/epsilon times, and this argument is basically doing Aurora on the patched spanner. Right, recall that what Aurora actually proved is that you can make your solution to cross each edge 1/epsilon times. Okay, so now the algorithm is basically to add this randomly shifted quad 3, find the spanner, and patch the spanner, make it 1/epsilon 4 right, and let this crossing of this spanner and quad 3 determine these portals. And then what you basically do next is bottom-up dynamic programming for each cell. So what we have here is a cell of a quad 3, and there are these spanner edges, and they determine the portals. So we get rid of this spanner edges because we don't need them anymore. We then guess this 1/epsilon crossings out of 1/epsilon to the 4 portals, because that's the number of portals we have. We select them by these black rectangles, and then guess this matching, non-crossing matching on this 1/epsilon crossings. And yeah, that's it, right? The running time that we have is number of cells times number of states times the time to construct a spanner. They get rid of this extra log n here by considering something that is called compressed quad 3. And this compressed quad 3 has only linear number of cells. Number of states is 1/epsilon to the 4 plus 1/epsilon. Which is this expression that I've promised you. And the time to construct this light spanner is poly 1/epsilon times n log n. And this is where the running time of Aaron-Smith comes from. Any questions about Aaron-Smith algorithm?
I have a quick question about the construction of the spanner. So does the construction use the fact that you are working in a complete Euclidean graph, or would it work on any planar graph with edge weights?
It uses it.
Okay. Do you know if there are any constructions of such spanners for any planar graphs?
Doesn't Klein use it in his planar?
Yeah.
I think even H-3 graphs have spanners now for because of this Soda 2020 paper of Hank.
Yes, you probably are right. Yeah, I need to check this literature then. Yeah. Okay. Yeah. Thanks.
Anyway, all the spanner constructions need n-log n time, except of spanner of Bartel and Gottlieb, which we cannot actually use. And now let me argue why it's really hard to improve this idea of using spanners. So actually there are lower bounds on the spanners. Lee and Solomon in FODS 2019 show that any spanner must have big lightness, and this lightness determined how many portals do we have. So if we would have 1/epsilon portals here, then would be great, but this is 1/epsilon to the d, which in 2 dimensions is 2 already. It's pretty high. You can use something that is called Steiner's spanner. Well, what is a Steiner's spanner? Steiner's regular spanner was a subgraph of a graph, and now in the Steiner's spanner you are allowed to use this new extra Steiner points. And yes, currently in Sausage 2021, there is a Steiner spanner construction that has actually that much lightness as we would like to have, and using it would be great. Unfortunately, there is one problem with that, and that this patching this spanner, this lightness was that on average you basically have 1/epsilon crossing, but it may happen that it is actually super linear. So that's why Ryan Smith had this this patching construction, and this patching actually makes you add this 1/epsilon more times many portals. So even if you would have the spanner or Steiner spanner that has this many lightness, it is not really known how to get something below getting this many portals at the end by using this patching. So that's a drawback. And the second is that even using this in high dimensions is not trivial. You cannot buy the whole line when you are working in 3 dimensions. You have to do something more involved. And yeah, we had lots of crazy ideas how to deal with it, and nothing works. And we have scrapped that. Now I will tell you these new ideas that we are having. Any questions about Rasmith? Yeah, if you are confused about it, we will basically not use it anymore. Okay, let's see this new nice idea. So this is what Aurora is using. Aurora is having this curve, and either she puts log n/epsilon portals on it, or she buys this whole line. Right? That's what she did, if you recall correctly. And it happens when your curve is crossing it only once. When your curve is crossing it 3 times, then you also put log n/epsilon portals. When it's crossing it more than constant number of times, she puts this log n/epsilon portals. But when the true is crossing it more than 1/epsilon times, then she buys this whole line. What's our idea is to have some smooth trade-off between them, right? We are not putting maximum number of portals or the smallest number of portals. We are having some smooth trade-off between them. So in some situations we will put this less portals. We will put even less portals if the true is crossing a lot, and if the true is crossing it more than 1/epsilon times, we can also buy this whole line. When the true is crossing it only once, we have to be super precise, because we are thinking about this 1/epsilon epsilon crossing for this epsilon cost for one crossing, and then we are doing basically the same thing as Aurora. So to reiterate, when the tour is crossing this edge, we have to be super precise, and we put a lot of portals. When the tour is crossing, let's say half of 1/epsilon, we can afford to put a lot less portals. So the idea is basically, if the tour is crossing an edge k times, then what we can afford is actually to put 1/epsilon squared k portals. When k is constant, then it will be 1/epsilon squared. When k is close to 1/epsilon, we will put 1/epsilon portals, and they are all equispaced. We don't do anything basically. Yeah. That's all the idea. That's the whole new simple observation. Now, I want to tell you that it actually gives the improvement of drying time. But there is one technical detail. When there is only one crossing, then we actually don't then our sensitive patching doesn't work. We have to plot n/epsilon particles, but it's still fine. It's only one special case of k equal to b1, like this case. That's some drawback of our technique. But in the dynamic programming, you basically can guess this k and put g of k many equispace portals. Now that the running time holds, is that this g of k is actually 1 over epsilon squared k, and you are selecting this k many of them, and luckily it's only it's only single exponential in 1 over epsilon. That's really cool about it. Okay. Any questions about that? Okay. Let me define this structure.
Just to make sure, in the dynamic programming, you are looking at larger and larger cells, and the dynamic programming states tells you the case on the borders. Yes.
We will go through dynamic programming very rigorously, but
no.
That's what's going on.
Oh no. Okay. Yeah.
It will be quick. I have to define what we actually prove. So the tour is 1 over epsilon simple. If it crosses this quad 3 edge at this, if it crosses it at k times, then it will be only crossing it through this 1 over epsilon squared k portals. And that's similar to Aurora. Aurora had this here a log n over epsilon portals. And the structure theorem that we will have is that this doesn't increase your cost by too much. The increase of this cost is only epsilon times opt. Right, there is one technical detail that I have here. It's the technical detail that it doesn't work for k equal to b1. So if it crosses only once, then it has to cross at exactly the same point as this original true pi. Yeah, then it will be called 1 over epsilon simple. And our structure theorem will say that this tour will not cross through the portals when you have this 1 over, when you are crossing only once. It will only guarantee us that it can cross exactly at one point. So we will have to guess it somehow, but we will use this Aurora structure theorem to guarantee that it is only crossing through this 1 over log n over epsilon portals. And that is basically it. That's the structure theorem that we are having. Now, something that Michał doesn't want us to see is this what we get by doing this dynamic programming. And by doing this dynamic programming, it's slightly involved, but I will be quick here. We get the 2 to the 1 over epsilon n to the log n to the 5 times. That's something worse than what we have at the end, but it will be simple dynamic programming. So in the proof, we select this randomly selected quad tree, and what we do first is apply the structure theorem of Aurora. It will guarantee us that any crossing will go through one of the log n over epsilon portals, even if it crosses it only once. And now on top of that Aurora structure theorem, we will apply our structure theorem. And this application of Aurora structure theorem is only to get rid of this small technical issue with k equal to 1. And then we actually can do is this dynamic programming. So in the dynamic programming, what we will have is a quad 3 cell, a number of portal, and the margin on these portals. And it will basically have this many states. So it's n log n cells. The number of states is basically 1 over epsilon squared k choose k. It is just a bound. So we have to take the maximum of that. Or it can be log n over epsilon. And it can happen that we have log n over epsilon for all 4 cells of this quad 3 cell. That's why we have this 4 here. And when we have this margin on this, when we have selected this portal set to be 1 over epsilon, then this margin will be 2 to the 1 over epsilon. And this is basically 2 to the 1 over epsilon and to the log n5. All right, I was hopefully fast. There are lots of technical details. If you have seen Aurora dynamic programming, there's a couple technical details. So first thing is base case. It's slightly non-trivial because we will put there something that is called compressed closed tree, and this will allow us to reduce this number of cells to be n instead of n log n. And the second thing is that number of margins doesn't work in three dimensions even, right? That there is nothing that is called non-crossing margin in 3 dimensions. It can go without crossing. So we have to use something that is called rank-based approach, and it makes our dynamic programming more complicated. So if you want to sacrifice this big O of 1 in logarithm, then you can get rid of it. But if you want to have as fast algorithm as you want, we have to use this rank-based approach. And in case of k equal to 1, we can use actually this panel technique to get even this rank time. So it will be like linear in n, and it will on n log n factor will be only in this polynomial in 1 over epsilon factor, and it will be as fast as we can go from here. Unfortunately, this dependence on dimension is double exponential, but it's actually needed Trevisan showed that even in this dimension d that is larger than log n, it's appears hard. So double exponential in d is really required. Maybe you can get rid of what this d here, but getting rid of this, yeah. But it is optimal. What we complement this result is with the matching lower bound. So the algorithm that I presented you before, even without this whistles and bells of this compressed case and the rank-based approach, it's optimal in terms of 1 over epsilon. So you cannot get even below this 1 over epsilon to the d minus 1 in the dimensions. Right, so I have showed you the algorithm. Now let me tell you this very nice proof that we are having. Any questions about the previous section?
I just wanted to say that we are getting over time slowly.
Oh man.
Just wanted to point it out. Meaning, we are relaxed with respect to this, but we slowly should be converging to the conclusion.
Okay, two slides for the proof and 1 slide for the lower bound. Okay, the proof is very nice. So maybe you will appreciate it because previously it was 10 pages long. Now it's only like half of a page in the paper. It's not that nice for the dimensions, unfortunately. So we are having this curve. This pi is the optimum solution, and this capital F is the edge of a quad tree. Okay, and this set X is the set of crossings. So the crossings of F with this optimum tool. What I want to introduce to you is this notion of parent and proximity. So for a crossing X, the parent is the next left vertex that is crossing, and the proximity is just the distance between parent and the vertex. Okay, and what we are basically trying to show is that if we put these portals, these crossings are the portals. So we are also having this equispaced portals here. And now I will show you how we actually patch. So we will divide this set of crossings into the set of new points, which we call n. And there are basically the points that are having the next crossing to be epsilon times this length of this face. Okay? So these are the crossings that are new to each other. And the set, and we will connect them to the next crossing on this line. and the set G is the set of great distance between the crossing. And if the set is on the greater distance than epsilon times f, we will connect them to the closest portals. So this will be represented by these green arrows. Yeah, this set of parents doesn't work for this last crossing, so we will also put it into the G. Okay. And now our patching strategy is simple. We connect this near sets to the next to its parent and the set G to the closest portal, and use this Aurora patching lemma on each component. You may be confused now. That's why I prepared the other picture. The other picture is by Shandor. We are having these near sets and these vertices that are near and vertices that are at the greater distance, and we basically want to do this patching lemma of Aurora on this near set and then connect them to the portal through vertices in the great set. And we will pay basically this green distance here. So what we basically want to show bound is this blue region here. This is what we want to have the dual bound on. Okay, any questions about that? Okay, let's bound it, and you will see this as a magical proof. So this blue region is basically the sum of all black arrows and the sum of all the green arrows. So what is the sum of black arrows? It's basically the sum of the proximities of these vertices in the near set. And what is the bound on the green arrows? It's basically the distance between the portals times the number of green arrows. And so we have selected this G to be 1 over epsilon squared K, and the length of this tour is F. So the distance between portals is this term. What's nice now is that this doesn't depend on G, it's just the distance between portals. So we can basically get rid of this summation of x's, and we get this G squared here. What I want to do now is bound this G squared here, and we will use Cauchy-Schwarz that says that, okay, G squared is bounded by this function f times this reciprocal of this function f. It works for any function, so it will work for proximity function, and we have this inequality. And what is this now? That's pretty cool. That's basically this total length of this proximity is the total length of this whole face. It's a good bound, so we put it here. And yeah, that's our bound. It only works because when G is greater than 1, because this proximity is not defined. That is the big issue with our analysis for k equal to 1. But yeah, that's it. We put this G square over here, and we arrive at this crazy expression. You may be super confused now, but let's not give up. Let's get rid of all this and rewrite it. What we want to do is basically the same thing as Aurora did. So we want to somehow charge this cost to the crossing. So what is the contribution of the cost to one crossing? So if you look at this formula, then this contribution is pro of x when x is in the near set, right? If this crossing is in the near set, this contribution to the cost is pro of x. And if the crossing is in the G set, by just looking at this formula, it's epsilon times the length of this face squared divided by 1 over pro of x. This is just by looking at this formula. So let's define this function of the contribution of the cost. So I define this coefficient alpha I of x, and it will be this contribution of this cost when I have this when I have pro of x to be pro of x, if this crossing is in the near set, and this other expression when this is in the great set. And what I want to do is put this alpha i's here. I can do that. But let's now use this definition of what it means that this crossing is in this great set, and what it means if it is in the new set. it's basically this, that this pro of x is large or small. So I've put it here, and now I can put this alpha i's here. Now let me transform it even further. That I have this phi of x. I want to get rid of this and say it in terms of this theta function. So I will have that this alpha I will be this cost when this I is greater than theta or smaller than theta. Now we are basically done with the proof. Oh, I forgot to put the definition of the length of the phase here. Right, so what it means that this expected cost is large. So if you sum over all the lines, vertical and horizontal, this is a summation over vertical and horizontal line, and the expected cost on all these vertical and horizontal lines, yeah, this is just the expected cost, the summation of expected cost on all lines. And I've put here the definition of what it is the expected cost. It's the probability that something happens and the cost that it happens. I put here this cost when I sum over all the edges of a quad tree. But this line has several edges, but all of them can be summed. And I have this. It is just inclusion of this x's and of this alphas. So this is number of terms in this sum is just the weight of this two if you sum over all the vertical and horizontal lines. Yeah, what I want to plug in now is basically this probability that h has level I. This is just because we have selected the random quad tree. This is 2i over L. Let's plug it in, and what we are only left is plugging this alpha i's here. So let's plug it in. And it is basically when alpha was smaller than theta, it was pro of x, and when alpha was greater than theta, it was this. So I have had summation over theta. What I want to claim now is that this is of order epsilon. Okay. Why is that? Let's simplify it. So this doesn't depend on I. This doesn't depend on I. And we have this. And what is this? This is just a geometric series. So I can bound it by here. I can bound it by the last term. And the last term is epsilon L divided by pro of x, and L cancel out, and I have epsilon. And here the same happens, but in the reverse. So I have pro of x cancel out, L cancels out, and when epsilon cancels out, I have epsilon. And now I have proven that expected cost is epsilon times length of opt. Yeah, that's really compressing 10 pages into 2 slides. Any questions about this proof? You might be super confused now. Yeah, but at the end, what we do is something super non-trivial, and people have missed it for 20 years after Aurora, but you can do this. Click. Okay. Yeah, we are just heading to the lower bound, so I will show you it very quick. So we prove a Gap-ETH lower bound. Gap-ETH is basically the hypothesis that you cannot approximate SAT in sub-exponential time. The hardness for TSP follows basically from these existing constructions, and it's just going through and looking at the box what is happening here. But for the rectilinear Steiner tree, we do some new arguments. Because even only NP hardness was known, there was no even exact lower bound for rectilinear Steiner tree. The problem is that we cannot basically control this where the Steiner points are. We combine this graph embedding and group wiring theorem together to get this Gap-ETH lower bound. But yeah, we cannot do this for Steiner tree, and we leave it as our open problem. And these are the figures that we are having in the paper, just for advertisement. And to conclude, we give an efficient and simple randomized algorithm for several known problems. We prove upon this Rowan Smith and Bartel and Gottlieb recent paper, and we prove lower bounds that matches our rank term, and there are several questions like, can you get a deterministic algorithm, can you get a matching lower bound, or can you even use this sparsity sensitive packing for other problems? And that's it. Thank you.
Okay, thanks a lot. So maybe we can on 3, 2, 1 unmute ourselves and clap. So 3, 2, 1. Yeah, is there any very quick question to Karol? Okay, and maybe I have a very quick question. Can you actually reinterpret, because you are doing dynamic programming, basically going up the quad tree, could you construct some kind of a graph based on this quad tree and on the portals and cast your dynamic programming through as a dynamic programming on, say, a 3D composition on this graph?
You mean to get rid of the plane?
Yeah, to essentially abstract away.
Yes, you can, but you would get, I think, polynomial in an algorithm. I think you would get n to the 4 algorithm by using.
I see. Okay, so you can
subset TSP.
but okay,
You have to solve.
Okay, good.
You wouldn't get a nonlinear time.
Yeah, I don't care about nonlinear time. I do care about not losing the dependency on 1 over epsilon. But yeah. Okay, this was just to understand whether you can modularize this approach. Okay, good. Any more questions? If not, then thanks, Karol, again for the very nice talk, and yeah, thank you very much.